welcome you all to this course on defects in material. In the last class, we have talked about coordinate transformation and lattice correspondence. Why do we require this? As I mentioned, that quite often, especially in some of the experiments which we do, we will be measuring properties of the sample with respect to some coordinate system which corresponds to the sample coordinate system. But the property inherently may be decided by a coordinate system which corresponds to that of the material. For example, if we are trying to find out a texture in a material. So when we do a texture, what we are trying to do, we deform a sample and then we say that with respect to the sample, we decide that these are all the coordinates. That is, this is the rolling direction, okay, and this is the normal to the rolling direction, and then there is the third direction, the thickness which comes into the picture. So this is how we try to say with respect to these three directions, okay, we define that axis. But crystallographically, if we look at it, the orientation could be something else which is different. So how the material behaves depends upon the crystallographic orientation. So often we will have to go from one coordinate system to the other coordinate system, okay, to describe the properties. So if we see with respect to an external coordinate system, the sample coordinate system, depending upon the orientation in which the sample has been cut, the properties may be different. So if we have to interpret the properties, we should understand the property with respect to some coordinate system, which is essentially the crystallographic axis of the sample, and then we can try to represent the property in terms of the coordinate system which we are measuring. Okay, then interpretation becomes easy and we can have a better understanding of the properties of the material. I use the word the property. Okay. So now the question which comes is that, is the property independent of direction in the material, or could the property also dependent upon different directions? Okay. If the property is independent of the material, then it's an isotropic system, okay, and most of the material, the properties depend on directions. When we say it depends on direction, then what is it which is important? To represent directions, we have to choose a coordinate system and then tell that how the property changes. So that means that we have to choose an axis system, okay, and with respect to this axis system, we should tell how this property is varying. Correct? That's what is very much necessary. That is, that information if we have, okay, how the property is varying, and this property can be we can transform from the system in which crystallographically it is the crystallographic axis system with respect to it. If we define any other axis system, we can find out the transformation of the properties. Okay. So this property, when we describe in terms of this coordinate system, this is called as a tensor, okay, or a tensor is a property material. Now let us come back to the actual experiment. So essentially all these things which we do, this mathematical operation of tensors, is essentially to get information about the property. When we do any experiment, okay, what do? We just give some input signal, then we collect the output signal, this could be a simple thing like you apply a input, initially a voltage, the output signal which you collect, it is a current density. Then what does this information, the relationship between these two tell? Is what the resistivity or the conductivity of the material, that information. So conductivity is the property, the information which we get about is that by doing this experiment, giving an input signal and getting an output signal, we are getting information about the property. This happens in almost all experiments. Okay? Like for example, when we do an X-ray diffraction, what do? We put essentially incident X-ray in some particular direction and try to find out the X-ray which is scattered in various directions. That gives information about the scattering behavior of this material. That's a property of that sample. Okay. Similarly, the other experiment is, which I will come to shortly, is about in metallurgy about mechanical behavior. You try to find out the strain in the material. Okay. In this input and output signal, when we consider, with respect to the sample coordinate system, this input is maybe given in some specific direction. So it could be a vector. We are measuring the output in another direction. So that's also when it's direction specified, it becomes a vector. So the property which we measure is the one which relates between two vectors. Okay. So if we measure property between two vectors, this property in terms of the coordinate system when we represent, it requires some components along different directions. The property has to be known. So how many independent components which will be requiring is, which will come to know shortly, it's about 9. That is because when we define input signal, okay, as a vector, okay, it could be, I can just, as a general form, I can write it as P, okay. The output which I am measuring it is another vector Q. Then this has to be related through some property which I write it as T, right. Suppose P has components P1, P2, P3. Then Q also has component vectors Q1, Q2, Q3, because when we define a vector, any vector, if we take like this is P and this is Q, this P can be defined in terms of this coordinate system: component along the x-axis, component along the y-axis, and the component along the z-axis. So that is what P1, P2, P3. Similarly, Q also can be defined that way. So if this has to be connected, then this will be in terms of the property. If you look at it, essentially this can be written in the form of T11 into Q1 T13 into Q3 So essentially what we have done, the component of the vector P, okay, is measured in terms of Q1, Q2 and Q3, okay, which are components of A. In that specific direction, what is the property? That property we define as T11, T12, T13, correct? That is with respect to that P1. Similarly, we can write it for all. So this itself can be written in the form of a matrix. Right? In this way in which we can represent it. Okay. But what is important is that Q is a vector and P is also a vector, right? So let us come to this a little bit later. Okay. Now we talked about doing an experiment to measure the property. Okay. Suppose we do an experiment. Okay. For example, we are trying to measure the conductivity of a material. We apply a particular voltage. Okay. We take a sample which is a spherical sample. Okay. You apply a voltage in this direction, okay, and measure the current which is flowing through this in this particular one. We have taken a sphere of a material. Maybe this sample is of you assume to be a single crystal. Now I just fix a coordinate system with 3 axes, and with respect to which I am applying a voltage and measuring the current, and then I just go on changing the direction in which the voltage is being applied. Okay. You assume that I applied the same voltage and measure the current density which is in that direction. So if I measure it, now I can plot, okay, and each direction where a voltage is applied, I can measure the current. So in that direction, what is the actual resistance? From that I can find out the conductivity, and I can plot it with respect to a coordinate system which I have. If I try to plot this value, there are many options which are there. What are the ways in which this can happen? When I try to plot it, one, this can try to be, the conductivity itself can try to be an ellipsoid like this, with the maximum values coming, conductivity coming along the axis, or it can so happen that it can be an ellipsoid which is in this direction with respect to what we, because we do not know what the, depending upon the results, all possibilities are there. Okay. These are all the various ways in which the conductivity can come. A similar experiment which we can think of another is when we do a mechanical behavior, that is deformation of a material. Suppose we take a single crystal of a material, okay, and take a wire of that sample of a particular length, okay, and in different direction, the particular length in a different direction we have made a material. Now we apply the same load to that sample and try to measure what is going to be the elongation in each of the direction. Then we will find that in different directions, and the load which we are applying so small that the property which we measure, in the case of an elastic material, it is within the elastic regime, or in all this property measurement, what we assume is that the property remains the same, doesn't change by the application of any of the external signal onto the sample. Suppose it happens that if you apply a very large voltage, the rise in temperature can happen, then the properties can change, or the material itself can crack. There are so many things. So what we do it is that we apply signal of such a strength that it doesn't alter the property of the material, and that's what we are trying to find out in each of these cases. So if apply a load which is very small, we can find out what is going to be the elongation in each of the direction. And then if we try to, when we know that elongation, we can either plot displacement versus the direction with respect to which the load is applied, or we can plot strain with respect to the direction. Okay. Both are possible. Okay. That will give rise to some sort of an ellipsoid. We will be getting it similar to what we have observed in this particular case. Okay. Now the whole question is that what we have measured in this case is essentially an extension which is a displacement, and the position with respect to it we are changing it. So essentially two vectors which we are trying to relate it use, and the property is the strain which comes out. That is why we call strain as a tensor, and two vectors then we call it as a second rank tensor. Okay. So that means that in this one, to relate each component we should have three components of the independent properties in three directions in which the signal is being applied. That when we apply a signal, it has three components with respect to a coordinate system which you have chosen. With respect to that we should know the properties. So that means that since the output signal is also a vector, it has three components, totally 9 components will be there for a second rank tensor. Is it clear? Okay. Now, we have just talked about the property of the material. Okay. Now we mentioned that in many a time we require a coordinate transformation which will be required to measure the properties. Okay. Suppose we assume that this is the sort of a coordinate system which we are choosing it, and the black line represents the old coordinate system x, y, z, and the red line represents the new coordinate system. Okay. If then if we wanted to transform from one coordinate system to another, what we should know is that with respect to x dash coordinate, if we take it for example, what is going to be the its component, essentially its component in the x axis, y axis and the z axis of the old coordinate system. If we know that information, then we can represent this coordinate. So this, to represent this, what we require is nothing but that when we talk about the component of x dash in x, it means that projection of x dash into x, correct? So we should know the direction cosines which we should know. Then we can write an expression like this. Okay. This I mentioned yesterday, the last class. Okay. From this expression, we can get a relationship between x dash, y dash, z dash and x, y, z, correct? This is what we can get that information. Instead of mentioning these angles, okay, as cos alpha, it requires a lot of space and we have to remember the notation. Another simple method, as I mentioned in the last class, we can write it in terms of A1, A2, A3, right? If you do that, this vector is a dash can be written okay in this format. So you can refer to the last class what I had mentioned about this relationship between the old coordinate and the new coordinate system. Okay, that way we can represent them. Suppose now we have a vector which we define like this, the vector p. Okay, that means that if you do your transformation, the vector p is defined with respect to one coordinate system. Okay, the input signal. So when we are trying to do with respect to another coordinate system, then not only the properties but the vectors also will change their components, because the magnitude of the vector will remain the same, because it's only a rotation which is being implemented. But what is essentially is going to happen is that the components of the vector p with respect to old and the new coordinate system will change. Okay. If we represent this in terms of the new and the old coordinate system, suppose we represent p as is equal to I into j into p2 plus k into p3. Okay. And with respect to new coordinate system I dash P1 dash J dash P2 dash plus K dash P3 dash, correct? This is how the same vector is being represented. Okay. What will be the relationship between these two coordinate systems? Okay. Using this transformation of matrices we can get that. I will just write only the result, that is P1 dash will be equal to A11 plus A13 into P3 P2 dash equals A21 into P1 P3 dash equals A31 into P1 A32 into P2 plus A33 into P3. Okay. This can be written in a matrix format also. Okay. What is the way in which this can be represented? One is that this equation itself is, we have to write all the components, right? Is it, what is the short form in which we can write it? P1 dash will be written as equal to sigma j equals 1 to 3 A1j Pj. I can write it this form, correct? This clear? In this form also it can be written. If I write it in this one, suppose all the three components, here the component P1, P2, P3, it is varying. If I have to represent this also, this I use another suffix I, so then I will write Pi dash, okay. I have to write it that will be equal to, no, okay, just before that let us see that. It can be written in this form, correct? What is the Einstein convention he did was that when we have to write expressions in this particular format, okay, what is the method in which we can simplify it further? Okay. So he said that whichever is the suffix which is repeating, okay, that you call it as the dummy suffix. Okay. This itself is inherently, we can write it as assumption that this itself is equal to A1j Pj. That is, when these two suffixes we put it, and when that suffix repeat in a term, it implies that there is a summation over that. Okay. So we don't have to put this summation symbol, need not be mentioned at all. We don't have to explicitly put that symbol, write that symbol. Okay. Then another is, this summation symbol is nothing but the one, okay, which only shows that something which is getting repeated. So there is no need that you can do it any symbol. This itself can be written as, instead of it, I can write as well as A1k Pk also I can write it. Because when I expand it, what it happens, k will be from 1 to 3, so this will become finally A11 P1 plus A12 P2 plus A13 P3, right? Whether I use J or K, it does not matter. So that is why we call this as a dummy suffix. Is this clear? Okay. And then this expression can be written as that. This also the suffix is changing, so we will write it as pi dash can be written as a I j pj. This form we can write it, right? Then the expression for the components of the vector is completely defined. So in a very short form, 3 equations involving 9 components can be described using this one single equation, correct? This is essentially what is being followed in many of this tensor mathematics. Okay. If we understand this, then most of the work involving tensor algebra becomes much simpler. Okay. Is this clear? Correct? Okay. If this is clear, okay, now let us come back to the properties with respect to experiment which we are doing it. Okay. What I will do it is, now I will just clear this so that we have space for writing, or P, or this can be, you can write it as J, it does not matter. Okay. So these are all the components, correct? Q equals I into Q1 plus J into Q2 plus K into Q3, correct? So what does P1 represent? Essentially the component in the direction I, right? This now how will we write this in the form of a vector? So we have to write it in form of the components, na? Like this way we can write it. So that means that if we substitute this, then what it will happen? Okay, the vector P will be equal to, okay, I into T11 into Q1 Q2 plus T13 into Q3, correct? Plus J into the P2's component T21 into Q1 plus T22 into Q2 plus T23 into Q3 plus K into T31 into Q1 plus T32 into Q2 plus T33 into Q3, correct? This is how it will turn out to be. Now, we know that Q is also a vector, right? Suppose we wanted to write it in terms of that, okay, then what is the way in which this could be written? Okay. One way in which it could be written is equal to, okay, okay, then T12 into Ij, okay, plus T13 into Ik plus T21 into Ji plus T22 into jj, okay, here, plus T23 into jk plus T31 into ki, T32 into kj plus T33 into kk, okay, into a dot I can write I into q1 plus I into j into q2 plus k into q3. This form I can write it. Here instead, if you take the dot product like a normal vector, take these two, I dot I, what it will turn out to be 1. So this will become T11 into I into q1. Similarly, when we write it, finally we will be ending up in an expression of this type. Okay. See, you can see that I into q1, right, T into this into I into q2, correct, T into I into q3. So if you take the I out, this becomes like a term like this. Which one? No, this is P is the vector. P has the component P1, P2, P3. These are all the components of P1, P2, P3 in terms of Q. Now I am just, P can be written as a vector, I into, we can substitute it. That's what we have done that. So the vector P is defined. Okay. But Q1, Q2, Q3 is also a vector. Suppose we wanted to write in terms of the relationship between the two vectors, how do we write? Okay. So what I have taken is that here we are just putting it that this is two unit vectors, I into I. Okay. Then if you write it in terms of that and then put a dot, then I dot I will turn out to be 1. So what we will be ending up with will be the first term will be like this. So if you take I out, it becomes similar to this one, correct? So what we have now done is we have written this as an operator, okay, that is P is equal to an operator T, okay, it's like a dot product. This is between an operator and this one Q. This way writing it is laborious and tedious, okay. What is the way in which we can write it? That is, this itself can be written in terms of the component. That's why we write it in the form that if it is P1, P2, P3, this is only for the components which we are writing it, right? This is that actual detailed way in which if the vector has to be written, we have to write it this way. Suppose we find that that's a transformation which we have to undergo to correspond it with respect to a property which we measure in a new coordinate system. Then how will we represent this? We will represent, that is, if the vector P becomes P dash, okay, in the new coordinate system, and the vector Q becomes Q dash, and the vector T becomes T dash. Okay. But still this relationship has to be maintained. Correct? Now we know the relationship between P dash between the old and the new coordinate system we know. between the q we know the between the old and the new coordinate system. And how is it being done? Right at the beginning when we wrote about this, we mentioned that the vectors also I, j, k also become a corresponding vector, correct? That's a change which is going to be there, I dash, j dash and k dash in the new system. Between the old and the new coordinate system, okay, this is how we can represent the unit vectors also can be represented using a transformation matrix, correct? This is from the old to new, this is from new to old, okay. Suppose in this equation itself we wanted to do the transformation, okay, then what it will happen, this p what we have written it here is nothing but I into p1, right, plus j into p2 plus k into p3, okay. When we have to transform this to the new coordinate system, essentially how many components which we will have when it is transformed? We require essentially 9 terms will be there in that transformation, right? Is it not? Because p equals I into p1 plus j into p2 plus k into p3, okay. And if we take in p dash, it becomes I dash into p dash 1 plus j dash into p dash 2 plus k into p dash 3, right? We can substitute, we have to substitute for, if you wanted to transform into a old coordinate system, what we should do it, okay, we can substitute for this I dash, okay, and p dash. So when we do that, we end up with terms which are going to be the transformation. Finally, we will be getting the p1, p2, p3, we are going to get it, but the number of terms. Now let us look at, similarly it will happen with respect to q also, when we undergo a transformation from one to the other, correct? Here this is the property, this is II. I can be written in terms of I dash and j dash. Let us just look at only what is going to happen with respect to a components, okay. In terms of the new coordinate system, it will be in terms of I should be written in terms of I dash and j dash. So each one of them, if we substitute, there will be three, so essentially 9. So we have already 9 terms are there. So totally the number of things going on to be essentially 81. Okay. So this way of, this is very exact, you get the correct answer, but the number of terms becomes very large. Okay. So is there any way in which this could be simplified and written? Okay. So in fact in this one, if you try to look at any specific coefficient, let us just look at that. Suppose we look at T13, it is Ik, correct? And I and k, if we substitute for that in terms of these coefficients, okay. How many it's going to be? A11 I dash plus A21 J dash plus A31 K dash, correct? Into A13 I dash plus A23 J dash plus A33 K dash, correct? All these operations when we do. So now itself you can remember that T1 and T2, these are all the components which are going to be there, correct? If you have to relate between this and the old one, what we have to take finally, okay? This is T13 we are taking, it's the component. If you wanted to take T dash 13, then we have to take with respect to components which correspond to I dash and K dash only has to be taken, correct? So here I dash and K dash, the components are there. This if we try to do it, okay, what it will turn out to be, I will just write that expression only. A31 T11, because here we are taking it, this is the product. When we take it, that some of the terms will remain, the other terms will go. So we are only taking that IK, we are leaving it out, only the okay. Into A32 T2 plus A13 into A12 A33 into T23 plus A13 into A31 into T31 plus A13 into A32 into T32 plus A13 into A33 into T33. So essentially we have a, with respect to a old one, for each of the new component of the tensor we have 9 which is going to be there. Okay. Not only that, you can see that from the coordinate transformation matrix which we use, this is getting repeated, correct? Is it correct? Okay. This way it can be done. So for all other 9 components we can write it. We will have around essentially 81. This is going to be a very laborious way of doing it. So if we use the Einstein notation, then the job becomes much simpler, right? So how can we go about and do it? So the expression which we write it is that P dash equals T dash into Q dash, right? How can you do this transformation? First, P dash, okay, let us look at this P dash itself. It can be written in terms of the transformation matrix, right? If you take a component 1 into, I can write it in this form. right? Now, what is the way in which pk can be written? Pk is in the whole coordinate system. So, we can write this component pk is equal to ak L, I can write it as Q L, I can write it, because this is only a dummy suffix, correct? No, this will be T, this will be TKL, correct? This is how this relation, because that is P dash, we have transformed it into a whole coordinate, and then it's written in terms of P. P is related to Q in the whole transformation using this vector P equals T into Q. So, we can write it in terms of this one. This represents vector. So, now this will become equal to AIK, right, TKL into QL. Is it clear? Now, how can you write QL? That is, QL is now we transform it from this to the new coordinate system. So, then QL becomes ALJ, I think QJ dash, correct? No, this will be AJL. This is because that when we change that index will change, correct? Because one is the transpose of the other. So, QL becomes AJL into QJ dash. This right? Now, we substitute for this, then this expression becomes AIK, okay, TKL, AJL, QJ dash, right. Now, if we look at it, this is PI dash equals IK TKL into QJ dash it has become. Is it not now? So, that means that if we write the relationship between this vector and this vector, how exactly this relationship is going to come with respect to a coordinate system which we have considered here. This will be Pi dash equals, okay, T I J dash Q J dash. This clear? So, now T I J dash equals AIK TKL AJL. Actually, here we can write it in the order does not matter. So, we can write it as AIK AJL into TKL. Okay. This is the form in which we can write it. So, now we have got a handle to represent it. So, in this term, what are the indices which are repeating? Okay, K and L. No, Yeah, K and L are the dummies. Okay. Now if you try to expand this, okay, with respect to, let us take 1, 3. Okay, let us see what it happens. Okay. That means that I and J turns out to be 1 and 3, right? A, K, A, 3, L, TKL, correct? Because if we take for a space, this will be equal to, suppose first let us take it with respect to L. Then what it will happen? A1K, A31, TK, this will be 1, because we are taking L changing from 1 to 3, plus A1K, A32, okay, TK is from 2, correct, plus A1K, A33, TK 3. Now let us do for the indices K. Then what is going to happen? A11, A31, 11, 11, A32, T12, A3, T13, okay, plus, yeah, yes, yeah, yeah, 2, 3, yeah, okay, T33. So now if you look at it, this and this are essentially identical, but in this simple one expression we can write it, right? From this we can make out that this is the easy way in which we can do transformation from one component to another component. Okay. So in this class, so far what we have looked at is the coordinate transformation. Okay. What is the relationship between the vectors, which is governed by the property which decides the connection between the vectors. Then if we represent the vectors in terms of some coordinate system, then the property also is component should be there in terms in those directions. Those components are essentially 9, which is required, because otherwise if you take a matrix 3 by 1 matrix and another 3 by 1 matrix, if you have to relate by a matrix, it has to be a 3 by 3 matrix, which is a property matrix. This rule we can do it if it is going to be a 4 by 1 matrix, if a vector we represent it in some 4-dimensional space, the other vector is going to be 4 by 1, then the number of components of the tensor will be 16 will be there, correct? Is it clear? Okay. So now what we have done it is that we have written these vectors, correct? So this is the form in which this vector could be written. These 9 components of this vector, is it that this vector has to be symmetric? No, there need not be. All the 9 components could have different values. It need not be a symmetric vector. But no, this tensor need not be vector. The components of this tensor operator, okay, this matrix need not be a symmetric tensor. Okay, but a tensor which is not symmetric, we can write it in as a symmetric tensor, as a sum of symmetric and an antisymmetric tensor. That can very easily be done. Okay. Then if we do it, how will it turn out to be? This vector, that is, if a tensor, we write it as T, okay, with components Tij representing this component, then we can write it that Tij half into Tij plus Tji, okay, plus half into j minus t. This form, if you write it, this is a symmetric tensor, this is a asymmetric tensor. Okay, this form we can write it. And the symmetric part of the tensor, if we represent it, that symmetric part can be written in terms of, because it involves again 9 elements are there, diagonal elements and off diagonal elements are there. Okay. Like for example, if we consider this to be a strain matrix, so the diagonal elements represent essentially the principal pure strain, that is dilatational, and the others represent the shear strain, right. So any matrix in this form can be represented in another way. In a diagonal matrix we can represent it, so that if we represent this matrix, symmetric matrix as S, if we use the notation to do that, as symmetric matrix as A, then these components can be written as Sij, correct? So if you write it in terms of a diagonal matrix, it will become S11, that is, if we are looking for the property of this material, that is the tensor, okay, in some direction, okay, this tensor itself can be written in terms of principal components. What do we understand? Okay. Let us take an example with respect to a strain itself. Suppose we take as a strain as a matrix, okay, and we represent it in terms of Eij, okay, that strain can be written as E23. Okay. This is a symmetric tensor. Okay. These are all the shear components, this is the dilatation, correct? If we take a sample which contains all these components, that means that what it means, if we take a cube and if the shear stress and all these stresses are being applied, it changes into a parallelepiped. The shape change is going to be there, and there is going to be a volume change also. When we say in terms of a principal component, what we means is that by applying only the dilatational, that is either a compression or extension along some directions, the same volume and the shape change could be obtained without involving a shear strain itself to a sample which we can do it. How can we think of that? Okay. Let us take just a square. This square, if I apply a shear strain, just a shear strain, this is how the square will be turned into, correct? The same thing can be obtained by applying just compression in this direction and the tension in this direction. We can make it into this shape. That means that along some axis, we are only applying dilatational, we can obtain the same shape change. That means that the same shape which has been obtained with respect to a strain tensor which contains dilatation and shear strain, in some direction we can apply dilatation and shear components and do that. The same shape change with the same volume change could be obtained. Okay. So that is what essentially means that now these are all the diagonal way we can represent it. Now this itself can be represented to represent the property in this axis. That is, we can choose this as the axis, one axis, principal axis, another these are all axes which are perpendicular to each other. So if we represent the property choosing this principal axis, okay, then the other components are going to be 0, right? Okay. So far now we have covered how to relationship, that is the coordinate transformation, relationship between different vectors which are connected by property, okay, how to transform from one coordinate system to the other, okay, and the symmetric tensor we understood that it can be written in terms of principal components, okay. This way we can write it. Okay. Now next we will take an example and how this information which you have gained could be used to explain what we started with a property measurement, how it could be done in the next class.